Hello and welcome back. This is post midterm, so we'll be starting on our next major topic, which is graph algorithms. Remember that we are online. If you have questions, go ahead and post to Piazza. You can also go ahead and comment in the YouTube stream. All right, so first of all, so you're probably familiar with a little bit of graph theory already, but I did want to make sure that we're all on the same page here. There are lots of different types of graphs. We're going to focus in on only a few types. All right. For example, undirected graphs. Right. Where you have vertices and edges that have no the edges, excuse me, have no orientation. That is, if I've got a vertex or an edge connecting x and y, that's the same thing as connecting y to x. Right. So you do, if you have an undirected graph, depending on your representation of that graph, you do have to consider that it's basically symmetric. You also have directed graphs, right? Edges do have an orientation, right? That x comma y refers to an edge where I've got x oriented towards y, right? But not necessarily the other way, right? That would be two edges, right? If you've got go from x to y, if you also have y to x, then you would generally draw those and represent those as two separate edges. You can also have weighted versus unweighted graphs, right? So graphs that are weighted, generally, each edge may have a weight that is a numerical value associated with it. It could be an integer, or it could be negative, it could be zero, whatever. Basically, it models a cost of some sort. If you want to go from edge x to y, it's going to cost you whatever the weight of that edge is, or maybe a distance, or some other resource measure that you're trying to model. Right? Unweighted graphs can be seen as weighted graphs with uniform weights of 1, right? So in other words, you can just consider weighted graphs, and then if you have an unweighted graph, you can cast that as a weighted graph by simply just assigning a 1 value to all their edges. From going from x to y, it costs you 1, whatever that means, $1, or 1 iteration, or something like that, right? There are many ways to represent graphs, right? There are adjacency, several. I shouldn't say many, but adjacency matrices, or adjacency lists, or maps, or sets of pairs of vertices, right? That is a set of edges, right? So there are lots of ways that you could, potentially go about programming your solutions for the next assignment. What I want to do is I want to remind you of what each one, at least the first two, of what that would look like if you want to roll your own and design your own graph class or graph or node class along with that. You may have already done that with Huffman coding, for example. Here's a somewhat large graph. It has 9 vertices. So with an adjacency matrix, it would end up being a 9 for this particular example. In general, it's going to be n by n. But for this example, it's going to be 9 by 9. And since it's unweighted, we'll simply just use Boolean values, true and false. I'll substitute in 0 and 1 for edges. What we do is we order the vertices. In general, it's a set, so they're not ordered generally. But we'll go ahead and impose an ordering on them so that we can write them on the right-hand side here. And I'll give myself some more room over here. A, B, C, D, E, F, G, ... I'm not going to go all the way there. But I will do a little bit of them. A, B, C, D, ... All right. So along the diagonal of this matrix, everything can be considered connected to itself. So for example, A If you're already at A, it's already there. Now, some graph representations allow you to have what are called self loops, like I just drew. The self loop means that you can go ahead and loop around A. That might come with some cost associated with it, right? It costs you 5 units to stay here, or something like that. We're not going to do that. We're not going to consider self loops in graphs. So we're essentially going to ignore the diagonal. You can go ahead if it helps, and from a practical perspective, you can say that A is connected to A because you're already there, and just go ahead and put 1s on the diagonal. Since this is an undirected graph, you can imagine that this is going to be a symmetric matrix. So since B and A are connected, I can put a 1 here, and then along on the other side of the diagonal, B is connected to A, so I'll go ahead and put a 1 there. Right? A is also connected to C, but A is not connected to D, so I would put a 0 there. Right? In general, again, it's going to be a 1 if the edge is present, 0 otherwise. Right? And that's the idea behind an adjacency matrix. I'm not going to fill this out because it would be 81 different entries. But if you want to represent your graph as an adjacency matrix, then you can do something like this. Now, these are Boolean values. You can also represent a weighted graph by replacing those Boolean values with the actual weight. So for example, if the edge from A to B had a weight of 5, then what you can do, instead of putting in a 1, you can put in a 5 there to keep track of the weight. All right? An alternative is to use an adjacency list. So for that, what you do is you establish n linked lists, each one associated with one of the vertices. So let's look at A's linked list. What we're going to do is we're going to put into this linked list all the neighbors of A. So A is connected to B, C, I, and H. Right? Note here that I intentionally, at least I am now claiming that I intentionally made these out of order. H becomes lexicographically H comes before I, because you can't necessarily, I mean, if you want to, you can of course make this into a sorted linked list, in which you do impose an ordering on it. But generally, who cares, right? There's an edge, X, Y is an edge, if and only if the list for Y, X contains Y, and or, right? The list for Y contains X. Right? I say and or because, again, there's a symmetry there. You could model a directed graph by interpreting that as if it's that A is connected to B with a directed edge if B is in A's list. But in B's list, if I don't put A, then this back edge here is not present. Right? Or you could go make an interpretation another way, where it can be in one list or the other, or both. It doesn't matter. That edge is there no matter what. Right? But B is connected to A, C, D, G, H. A, C, D, G, H. Right? And so I would put that into a big linked list there. Right? I's linked list would look something like A and F. Right? And again, symmetry. Are you going to put A in I's list, and are you going to put I in A's list? It depends on what you're trying to accomplish. Okay? So those are two ways of, and there are a couple more that I won't go over, but those are two ways of representing a graph. What I want to do is tell you, don't roll your own, right? Just like you don't write your own sorting algorithms. My recommendation is whenever you're doing graph stuff, as long as you're allowed to, in a class you may not be allowed to use a library or something like that, but my recommendation is use a library. Right? Now, for your assignment 3, you will be allowed to use a library to make it easy to represent the graph. If the library contains graph algorithms that you can use, you go ahead and feel free to use those to check your solution, but ultimately you will not be allowed to use those built-in algorithms in the library to formulate your solution. So yes, use a library, but do not use a library to the extent that it makes it trivial. All right. My recommendation for if you're using Python is networkx. Right. So if you just do a Google search, it's already installed on the CSE web server, networkx Python, right? And it is a graph library. It's not a graphing library. When you go to search for libraries, unfortunately, you'll get a bunch of libraries that allow you to draw graphs, right? X squared is this parabola. That's not what we're talking about. You'd have to search for graph theory or graph algorithm library for the particular language that you're using. For networkx, you can download it using pip if you want to. Otherwise, again, it's already installed on CSE. There's a nice little tutorial here that you can go ahead and check out and look at its basic usage. What I'm going to do is I'm going to show you a few of the things that that I would use. Right. So there's the tutorial. How do you create a graph, etc. So let me go ahead and quit out of that because it is slowing down my computer. All right. So hopefully there we go. Hopefully that's a little bit better. You have to import it, of course. So import networkx as NX is usually what it is. We get networkx short, NX is short for that. You can go ahead and create a graph by default. It's going to create an undirected, unweighted graph. Right? If you want to, you can add nodes to it. G.add node, right? 1. Now you could put in strings there. You could put in a string representation of a particular node. Now inside that node, hello is going to be stored. I'm just going to go ahead and create a graph with a single vertex here that's labeled 0. Doing that multiple times is not going to have an effect because the vertex 0 is already there. But of course, you can go ahead and generally what we do in your homework is we identify all the vertices 0 through n-1. Whenever we write it out in pseudocode, we of course identify them as 1 through n, but because you might want to use in programming, we always use indexing, and you might want to use an adjacency matrix representation. We're going to go ahead and go with identifying the number of vertices 0 to n-1. All right. You can also add multiple nodes. G.add nodes from. And then you can provide it an entire list instead, right? That would be equivalent to what I just did here. Or you could build an array using a list comprehension and add all the nodes from that, right? So both of those are options. Once you've got your nodes, of course, you can add edges. G.add edge, right? Surprise, surprise. I want to connect the vertex 0 to the vertex 2, right? G.add edge. I'll connect vertex 2 to 1. Right? And remember, this is an undirected graph by default. If you want a directed graph, you'd have to refer to the documentation on how to do that. So 1, 2 is the same thing as 2, 1. Right? G.add edge. So I'm going to 0 to 2, 2 to 1. I'll go from 0 to 1 as well. And then I'll add one more edge here from, say, 2 to 3. So I've got I've got a graph here with 4 vertices and 4 edges. What does it look like? Well, unfortunately, it's not as I mean, there are ways that there are add-on libraries, I should say, that plug into networkx and will produce like a PNG or a GIF of your graph so that you can take a look at it. I've written my own, networkx to LaTeX source so that I can, I don't have to do any work. I can for the handouts, I just create this graph and I throw it out there. But what would that ultimately look like? So taking a snapshot of that if you want to. Then what does it look like when I write it out? Well, I've got these vertices here, 0, 1, 2, and 3, right? And I've connected 0 to 2. I've connected 2 to 1. I've connected 0 to 1, and I've connected 2 to 3. So it looks something like this. It has a cycle, right? So it's not a tree, and it has 1, 2, 3, 4 vertices and 1, 2, 3, 4 edges. So that's what it's going to end up looking like when you if you have a printed representation of it. Of course, this is for graph algorithms. So the networkx library is not really concerning. Its primary concern is not creating these beautiful diagrams of your graphs. Instead, it's let's implement some algorithms on it. So of course, you might have access to, say, g dot number of nodes. How many nodes are in there, because you want to put that into a loop to iterate over each one of them, right? G dot number of edges, right? And you can print these out. I'll show you what that this is actually working, and that I've got actually available on my computer here. Let me give myself some more room here. Excuse me. There we go. All right. So I'm just going to run this demo here. Right. Oops. MX. NX. There we go. And you can see that the number of edges here and the number of nodes is going to be 4 and 4 respectively. Of course, if you want to iterate over those nodes, you can easily do that in a for loop for u in g.nodes, right? Print u. And that'll print all the nodes, not necessarily in order, but in this case it was in order. Right, well, that's probably because that's the order that I added them in. You can also iterate over edges for e in g.edges, right? Print e, right? And that's going to be a bunch of tuples. 0 to 2, 0, 1, and that is not the order that I put them in. So again, the vertex set, the edge set, they're being treated as sets, unordered collections. If you want to, you can use other syntax here. You can use, this unboxing or whatever they call it in Python, where you've got, because the edge is a tuple, you can go ahead and assign it to variables u and v, and then you can print whatever you want connects to v. There we go. And I get that representation instead. Right? You can do simple questions of whether or not there is an edge. For example, g.has edge, right? 0 to 3, right? Is that an edge, true or false? And you'll note up here that I did not put in 0 to 3, so this is going to print out false. Right? And let's test for something that was an edge. I did put in 0 to 2, so that's going to print out true. Right? There you go. So that's the very basics to get you started using networkx if you're choosing to use Python and if you're choosing to use this library. You want to roll your own, be my guest. You want to use a different programming language, be my guest. If you have suggestions on graph libraries out there for the particular language you're using, go ahead and post to Piazza. Right? Okay. So that's my recommendation. No questions still. So let me take a step backwards here, and let me justify why this is given its entirely own module, right? Usually I do this in, say, a 235 class or a 156 class, CS1 or discrete math or something. Why graph algorithms? Right? Or more generally, why graphs, right? And the reason, hopefully, is clear to you after a year of computer science. It's a modeling language, basically. Everything is a graph. If you have entities and you have relationships between those entities, then that's a graph, right? When you design a database, you design it with tables and relationships between those tables, and you generate an ER diagram. An ER diagram is a graph. A UML diagram is a graph. Chemical compounds are drawn on a piece of paper with various connections between various atoms, so showing an ionic connection or whatever it is, right? It's a graph, right? Graphs are basically universal languages because of relations. Hopefully you may remember binary relations from 235 from a discrete math. Binary relations are a generalization of graphs, and so graphs basically are relations. Relations are graphs, and relations can capture a whole slew of real-world problems. So if all these problems can be modeled as a graph, then if we develop one graph algorithm, that can be applied to all of those applications. And that's why graph algorithms and graph theory is so fundamental and important, because if you find a truth or if you find a theorem or something like that with respect to graphs and graph theory, then you've found a universal truth that can then be applied potentially to many, many different types of applications. Okay? So we need some fundamentals first, right? I just hopefully filled in the gap of the fundamentals. But what I mean is we need a fundamental algorithm to start out with. And given a graph, of course, you can iterate over the vertices. You can iterate over the edge set. But you want to really pay attention to what's called the topology of the graph, right? Just iterating over the vertices and edge set, that doesn't tell you anything about the connectivity of the graph. You want to explore the graph, right? Because the graph represents something and you're searching through the graph for a particular item, say. And so our first algorithm is going to be depth first search. Right? This is a fundamental algorithm. Shortened up, it's going to be DFS. It searches a graph as deeply as possible. So what do we mean by searching? Well, the way that we're going to present it is simply you're going over, you're finding all the vertices, not just by iterating over the vertex set, but you're finding all the vertices by starting at a vertex and then traversing to the next vertex, the next vertex, the next vertex. You're walking around this graph based on its topology. Okay? And you're finding out, does this thing connect to that thing? What is its shortest path? What is its longest path? What is its least weighted path, right? Those are the kind of questions you answer by actually walking along it that are not completely apparent by simply just looking at the vertex set and looking at the edge set. DFS basically searches as deeply as possible before backtracking. Right? Now, hopefully this is already familiar to you. And in fact, when we looked at backtracking with respect to, say, the Hamiltonian path problem or the Hamiltonian cycle problem, what we were doing, we were doing a naive DFS, a depth first search. We were going as deep into the graph as possible. When we hit a dead end, then we backed up, right? And then we explored another area of the graph. But whereas what we did in the first part of this course, where we did a depth first search, brute force kind of approach to solving the Hamiltonian path problem, we don't want to do that here. We want to be efficient. We only want to, we're finding a particular node, or we're processing all the nodes, or we're doing something. We don't want to process the same node over and over and over an exponential number of times. So DFS is going to have to be, our DFS is going to have to be catered so that we don't make all those repeated steps over and over and over again, okay? Basically, we want to make sure that we make progress. We want to make sure that we make progress. We only want to visit or process a node vertex more at most once, right? We don't want to get stuck in a loop. We certainly don't want to get stuck in an infinite loop. If there's like a cycle, we don't want to keep going around and around and around. But certainly we don't want to visit the same node and process it multiple times or an exponential number of times. We wanted to do that with Hamiltonian path because we were searching for a particular type of path, the longest path. Okay. You're already familiar with this, not only from this course at the beginning, but also from Computer Science 2, say. Tree traversal algorithms. Pre-order, post-order, and in-order are all DFS variants. Right? They only vary on when you process the node. Do you process it the first time that you visit it? Do you process it coming back from the left child? Do you process it coming back from the right child? That gives you a pre-order, in-order, and post-order respectively. What we're going to want to do is, though, when we want a DFS that works for any graph, not just trees, not just specifically binary trees, but we want to make it work for all graphs, right? And again, the idea is that we go as deep as possible until we hit a dead end. But along the way, we're going to keep track of vital information. Right? Have you visited this vertex before? Right? Have you visited all of its neighbors? Right? Have you processed this vertex already? Right? When did you first see this vertex? When did you last see it? Right? And throughout this entire process, we're going to use something very, very old from fairy tales, breadcrumbs, right? We want to know where we came from, where we've been, and so we're going to lay down breadcrumbs just like Hansel and Gretel, going deep into the forest so that they can find their way back out again, right? Or if you're in a maze, right? You mark the maze to know which way you came from, and you've been here before, so now you're stuck in a circle or something like that, right? And of course, magic mazes will not allow you to do that, and erase your stuff or change it or whatever, right? So just to understand what I'm talking about here, I'm going to simulate DFS on that graph that I just showed you, that large graph. So let's come back over here to the tablet. And we'll get into the pseudocode here in a moment. But what I want to do is I want to keep track of, or I'm going to perform a DFS on this graph. And what I'm going to do is I'm going to do a dry run, and then we're going to come back and we're going to consider what information we need to keep track of in order to not repeat ourselves. So let's just suppose that we start at I here, okay? Where do we go next? I look at its neighborhood here, and I see both A and F, right? I could go to A or I could go to F. I just need some criteria to make that decision. So what criteria do we have? Let's just go ahead and say that we'll go to the lexicographically next vertex. So starting at I see A and F, and those are both options, but I'm going to go with the one that is first in lexicographic order, and I'll go over here to A, right? Now I look at A's neighborhood and I see I already came from I because there's a big, huge red glowing thing in my path here. That's my breadcrumb. That's where I came from. So I see C and B and H here. So I'll go ahead and go in order. And at this point, I'm going to go ahead and switch over to actual red here so that it persists. There we go. So let's go ahead and go to B because that's next in lexicographic order. Right? I look at its neighborhood all around. And I see that C, D, G, H, and A are there, but A has already been visited, right? Because it's got a red mark on it. So we'll go to the lexicographically next one, C, and likewise then D, then E, then F, right? And at this point, we look at our neighborhood here, and we see D. Oh, I already came from there. I'm looking back at my breadcrumbs that I laid, and I see that I've already visited D, right? And I see that I've already visited I because that's where I started. So I start to backtrack. Right? I come back to E. And there are no other unvisited choices. I've already explored D and I've already explored F because of these red marks here. So I backtrack again. And I see that I do have some options here. I can go ahead and go over to G and then over to H. Right? At which point I've explored the entire graph and I reverse all the way back to the beginning because there are no other options, okay? Now, that worked because I was able to draw on this graph, right? A dumb computer is not going to be able to draw on it to have some memory, so what we're going to have to do is we're going to have to help the computer, help the algorithm is what I mean, by keeping track of those breadcrumbs and other pieces of data. Where are we? What's the current vertex that we're at? Where did we come from? Looking at the neighborhood, did I already visit that vertex? Yes, no, okay, well, if not, then I could go ahead and go over there, right? If yes, okay, well, then I won't go over there because I don't want to repeat myself. So I'm going to keep track of a whole bunch of what are called artifacts. Actually, let me give myself some more room here. Uh, there we go. Nope, that's not what I wanted. But I can get it. There we go. And hopefully that looks familiar to you immediately. How do you keep track of breadcrumbs? How do you keep track of breadcrumbs in order, pre-order, or post-order? It's going to be a stack. Okay. But I'm also going to keep track of when I visited it. I'm going to keep track of when you first see a vertex, right? When you process a vertex. And for our purposes, I'll process it when I'm done with it. I'm going to, remember, DFS, I'm going to go as deep as possible into the graph. So I'm not going to immediately process it until I've exhausted all possibilities going down that area of the maze. When I come back and, okay, I hit a dead end, I came back, I went that way, I hit another dead end, I came back, and there are no other options for me other than retreating and backtracking. Now I will go ahead and process this node, right? I'm also going to keep track of a couple of colors. White, or in this case blue, because I've colored all the vertices blue, is going to be unvisited. Right? And my breadcrumbs, I'm going to leave one of two colors. Gray, I don't know if it's EY or AY, what the American spelling is. I think it's AY, I'm not sure. But what I visited, but not processed. All right? And then finally, black. It's going to be processed. So if I'm at a vertex and I look at its neighborhood and I see that there are some white vertices, that I can still go to those vertices. If I see gray vertices, I know, oh, I've visited that vertex before. I just haven't processed it. So it must be in the path that I came from. So I'm not gonna visit it again. And then black vertices are done. I don't need to look at that vertex anymore because it's already been processed. So those are the things that I'm going to keep track of. And I'm just going to do it graphically over here as we go through this process again. Right? So, and for the first two, the first time you discover it and the second time, the time that you process it, I'm also going to write those down. So I'm going to start at an arbitrary vertex. I'll start at I. Right? And what I'm going to do is I'm going to mark it with a discovery time. So 1 is going to be my discovery time. And the way that I'm going to do this, I'm going to do it with a discovery time and then a colon and the finishing time or the processing time. This is going to be finish. And so eventually I'm going to come back to this and process it. In fact, it'll be the last one I do because I'm going to explore the entire graph, go as deep as possible before I come back to the beginning. Right? But I'm also going to color this vertex. Here's my highlighter. Right? And I'm going to color it gray. Right? Because I visited it, but it's not yet processed. And I'm also going to keep track of where I've been by pushing it onto this stack right here. Right? And you will see how that works. This is basically going to be my breadcrumbs. It's going to keep track of that red path that I took throughout the graph. Okay? Okay. So I'm looking at its neighborhood, I's neighborhood here, and I see A and F, just like I did before. Let me go ahead and traverse over to A. When I do that, I'm going to push A down in here. And I'm going to mark it as I've discovered it at timestamp 2, at step 2. Okay? But I'm also going to color it gray. It has been visited, but not yet processed. Let's continue. I'm looking at A's neighborhood here now. Right? That includes I, by the way. But I don't go to I because it's colored now gray. Right? A dumb computer can see, what's this color? Gray? Okay, ignore it. What's its color? White. Then go ahead and that's a candidate, that's a candidate, that's a candidate. Which one do we go to now? I'll go ahead and go to the lexicographically next one, B. And I push that, and I mark that with another timestamp, 3. You'll note here that I'm just keeping track of a counter to do this. And I color it gray because now it's visited, but it's not yet processed. Let's continue. Let's go to looking at its neighborhood now. Right? I'm seeing A, C, D, G, F, H. And so I'll end up going to C, the lexicographically next one. Color it, timestamp it at 4, and push it. At this point, I would draw your attention to the stack over here. Now it truly is a bunch of breadcrumbs. I came from I to A to B to C. I, A, B, C. It's keeping track of where I have been so far, right? I haven't backtracked yet, so all of these things are still in this stack, yet to be processed, yet to be completed, basically. Right? All right, so let's continue. My only option here, unvisited option, I should say, is going from C to D. Going to A is an option, but you'll see that it's colored gray, and so I don't go to it. That's discovered at timestamp 5, and I color it gray. And of course, push it. Oops. Sorry. Push it onto the stack. I look at its neighborhood, and I've got a lot of choices now. I could go to unvisited vertices are going to be G, E, and F. But remember that we're going in lexicographically next order, so I'll go ahead and go to E, pushing it onto the stack and coloring it gray, marking it with the timestamp of 6. Okay. Next, I'll go on to F because that's my only choice. Mark it with a timestamp of 7 and color it gray. At that point, again, looking at its neighborhood here, I could go to E, I could go to D, I could go to I, but they're all gray, right? And so at that point, I'm done, right? What I do is now I start reversing, right? I pop this off the stack, right? And I process it. I also, you can use the same counter. You can use different counters if you want for discovery time and finish time, but I'm just going to use the same counter here, 8, right? And because it's been processed, I'm done with it entirely. I will now color this with a much darker black here as being done, right? There we go. I'll do 2 coats. You can see that this process is going to reverse itself until I've got other choices. What I'm going to do now is I'm going to pop off the next vertex because I have basically I'm at E now, right? I've backtracked. These were my breadcrumbs and I hit a dead end. So what do? I backtrack, and the way that I do that is by popping off the top and basically reversing. If I was stepping forward, now because I have no options, I pop that off the stack, and now effectively by looking at the top of the stack, which was E, I'm back at where I back one previous step. Right? That's why we use a stack. First in, last in, first out. Right? It keeps track of our immediate last step for us. I will process it, timestamp it at 9, and color it black because it's now done. Okay? I have to backtrack again. D, process. And its timestamp, finishing timestamp is 10. And I'm done with it. Actually, sorry, no. Sorry. Back up here. Restore this 5. There we go. Right. D. Now I'm back at D with a thing at the top of the stack. I failed to notice here that I do have options. Let's look at its neighborhood. I'm still at D here. I could go to C, I could go to B, but those are gray. I could go to F, I could go to E, or if that's what that is, but those are black. Those have already been processed. You don't want to go to it a second time and process it twice. But G over here is unvisited, white. So I will go ahead and push it. My timestamp now is 10, and I will highlight it as gray. Visited, but not yet processed. At G, I have another option. I could go to H, and so I do. Oh, needed to do that there too. And it's discovered at timestamp 11, and it also is highlighted in gray here. Now at that point, now I would draw your attention to the stack at this point. These are breadcrumbs, but they're not the same breadcrumbs as before. Remember that we went down this direction, but we hit a dead end, so we started to backtrack. At that point, the breadcrumbs are only keeping track of where I started and where I currently am. Right, so don't think of these breadcrumbs as giving you all of these black edges here that I've colored black. Right, instead it is a snapshot of your current position. Right, where you've been since the beginning of the algorithm. Okay. So as you can imagine, since we've already visited everything, things are going to start popping off here. H comes off the top, and we process it at timestamp 12. We end up coloring it black, right? And it's now gone. We come back to G. Oops. And now I do look at, before I process it, I look at its neighborhood, right? I look at its neighborhood and I see a gray, and a black vertex. No other choices, so backtrack. By processing it at timestamp 13, coloring it black, oops, right, and popping it off the top. Okay. This is just going to reverse itself all the way through. 14, 15, 16, 17, and 18. Right? And each one of these got popped off the top, popped off the top, popped off the top until you reach the bottom. And each one of these things was ultimately colored black. Not in the order that I just did, but approximately. Right? And now our stack is empty. And that's how we know that we're done with the algorithm, for a connected graph at least. That while our stack, we continue this process of looking at the neighborhood, choosing a white unvisited vertex to go to, pushing that onto the stack. When I reverse the process, I'm popping things off the top of the stack. When I get back to where I started, the stack will be empty, and that's how I know that the algorithm is done. Okay? Okay. So let's go over the actual pseudocode here for this. Right. Now I'm going to show you the stack-based solution. If you want to, you can of course go to the lecture notes, and there is a recursive version that a lot of people present this as recursive. We did when we looked at this from a perspective of a Hamiltonian pathfinding algorithm, a brute force algorithm. I'm not going to do that here though, because a stack is much more elegant. You put stuff in, you take stuff out, right? Depending on the colors that you see around you. And by colors, of course, we mean you could just set a flag value. Visited, unvisited, and processed, right? And we use colors because we can't just use true and false. You have to use A, B, C, or 0, 1, 2, or an enumerated type is what I would do, right? So here's our stack-based pseudocode. My input is going to, of course, be an undirected graph. It'll work for a directed graph, by the way. You just have to, when you look at a neighborhood, you don't look at incoming edges. You only look at outgoing edges. V, comma, E. Right. So here's my initialization. What I need to do is for each vertex U in the vertex set, I'm going to initialize it by coloring it white. Color U white. That is unvisited. All right. I'm going to want a counter that I'll initialize to 1. All right. Remember that we were using the same counter for discovery times and finishing times. Each time we push something onto the stack or pop something off the stack, we incremented that counter so that we just look at the current counter, stamp, 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 right? And of course, I'm going to want to initialize a stack. Or here, I'll just call it S. new stack. Right? That's going to hold vertices. We got to get it started, so I will push our start vertex U. In fact, I'll just call it S here, onto S. I'm going to go ahead and short that as shorthand that I should say S dot push S. I've already used S, so I don't want to confuse that, so I'll use X, where X is the start vertex. And again, that criteria could be arbitrary. It could be the lexicographically first vertex. It could, if you want to have graphs can have weights on their vertices instead of their edges, or both. It could be the least weighted vertex. It could be the last vertex. It could just be some random vertex. It doesn't really matter. A DFS traversal will be different depending on your criteria for the next vertex choice. It will be different depending on where you start. But ultimately, all DFSs are going to search the entire graph, so it really doesn't matter. Right? I will mark X with discovery time equal to the counter. Right? And then I visited it, so I'm going to color X gray. And then I'm going to, and then that's it. This is the initialization here, right? I will mark this as initialization phase. I'm going to quickly run out of room here, so I'll go to the next slide. But otherwise, that's just the initialization. Then we've got this big giant loop. And this is, to give myself some more room here, I will go ahead and go to the next one here, right? So this is the big loop. While S is not empty, right? While our stack is not empty. And it's not empty here because of the initialization. Remember, we went ahead and pushed X, our starting vertex, onto the stack. If the graph were empty, well, then there'd be nothing to do. That's a special case that you can take care of separately, right? Or it'll be subsumed by this loop, and this loop would never execute, right? So I'm going to increment my counter because I want to timestamp it with the next timestamp. I will look at what's at the top of the stack. So remember that the basic stack implementation has push and pop. It's a last in, first out. But it's sometimes easy or makes your life easy if you have these other secondary pieces of functionality, and one of those being peek. Remember what that does. That looks at the thing at the top of the stack, the thing that would come out next in last in, first out order, but it doesn't take it off the stack. Right? It's still there. And that's basically where I am. This is your current vertex / location. Right? That's where I'm standing, basically. Right? Where do I want to go next? Choose the next vertex in n sub x. And remember, annotation here, this is the neighborhood of x, right? And I'm going to have to next, there we go, white vertex in the neighborhood, right? Remember, sometimes there will be gray vertices, there will be black vertices, but you want to go to the next unvisited vertex, right? So unvisited, right? If there is none, if y is none or nil or whatever, this is too Python-y here, but if there is no next vertex, do nothing, right? So I just wrote that so that as annotation here. I'll go ahead and keep it as a comment here. If y is nil, nothing, do nothing, right? that means that you will end the while loop and go right back up to the beginning. Otherwise, actually, sorry, let me be more formal about that. There we go. Because you will want to backtrack here. If y does not exist, let's say is, yeah, here, I'll use the special symbol phi here, right? There is no such y. There is no white vertex here. Then what we're going to do is that we need to backtrack. But before we backtrack, we need to take that thing off the top of the stack, right? So s dot pop. We don't need to capture that return value, by the way, because we've already peeked at it. We already have x. I'm just now formally removing it from the stack, right? We process x. We color x black, right? It's done. And we timestamp x's finish with counter, right? That's the backtracking. We're done with x. We take it off the top, and by taking it off the top of the stack, we've basically backed up one step in the process. Otherwise, and unfortunately I'm going to need 3 here, otherwise, we push it, s.push, maybe I don't need 3, y, right? In other words, we go to y. We go to the next thing in the neighborhood. Right? DFS, we're going as deep as possible here. We color y gray, right? Because it's now visited. We're stepping on it, and then we're going to process its neighborhood on the next iteration of this while loop. And then I'll just put it here, mark y's discovery time with counter. There. These are mutually exclusive, if and else, so we only use the counter once. And that's why we increment it at the top here. We only need to increment it before we do our next step, right? And that's it, right? Oh, let me go ahead and go back. All right, so any questions so far? No questions. So let's talk a little bit about, again, if you're interested in doing the recursive version, the notes have pseudocode for it. There is a gotcha there, and in fact with this implementation as well, that we'll talk about here in a moment. But otherwise, if you're interested in the recursive version, go ahead and check out the notes. I'm not going to cover it because this is way more elegant, right? Remember, if you didn't take my Computer Science 2 course, the theme of that is that smart data structures and dumb code are a lot better than the other way around. Smart data structure like a stack. It's not that smart, but it is elegant because it provides you a last in, first out manner of visiting things. You put stuff in, you take stuff out, and it gives you this nice, elegant algorithm for searching a graph, a depth first search. All right. Okay, so let's go ahead and go back to the notes here, and let's note some things. Gotchas. Here, I'll go like this. Can I go that deep? Gotchas. Or miscellaneous. All right. So DFS may need to be restarted at unvisited vertices if it is disconnected or if it is directed. Now, what do I mean by that? Well, imagine these a graph with 2 components. There are 3 vertices over here and 4 vertices over here, but there's no edge between these 2 components. These are all 4 of these are connected by some series of edges. These 3 are connected by some series of edges, but there's no connection between them, right? What might that look like? I'll go ahead and draw it really quick here. Right, so suppose that there's a connected component over here with 3 vertices, and over here, that's the graph that we drew at the very beginning, right? Something like this, right? But they're disconnected. If I performed a DFS on just one component, right? if I performed a DFS over on this component, ended up visiting, backtracking, visiting, backtracking, or then visiting over here, right? All of these over here are still unvisited. I would have to restart my DFS over here to visit all of these vertices. But also, DFS can then be used to determine, is your graph connected or not? Did you have to start your DFS over? Or after the conclusion of your DFS, were there white vertices, white unvisited vertices left over? If so, then true, your graph is disconnected, right? So you can use that to your advantage if you're trying to decide the topology of that graph, right? DFS can produce several other artifacts beyond just the timestamps, the discovery timestamp, and then the processing. Of course, what do we mean by processing, by the way? Ostensibly, you are storing data in your nodes. That data is being processed, right? That's a question. That's a you question. What are you storing in your graph, right? And why do you need to process it? When we say process, it's just a generic, all right, do whatever you're going to do with that data stored in that node, right? For our purposes, we're just going to keep that generic and abstract. But DFS can also produce several other artifacts. For example, a DFS for a tree or a forest, if it's disconnected. Right? So there are three types of edges that can come out of this. There are tree edges, right? Edges that are traversed via the DFS traversal. When you go from one vertex to another vertex via this edge, that ends up being a tree edge. Right? There are back edges, right? Edges that connect descendants in the DFS tree to an ancestor. Right? There are forward edges that connect an ancestor to a descendant. Right? And finally, there are cross edges that connect between cousins, other components, connect between components of a DFS tree, right? So what do I mean by that? Those aren't even rigorous definitions, but a picture is worth a lot more here. Okay, so what we're going to do is we're going to go back to our example over here, and in fact, most of this of the artifacts have already been done for us. Right? Remember, I used black here to indicate where we came from in the DFS traversal. So I'm going to write that all out. From I we went to A, and and then we went to B, right? Then we went to C. Each one of these things that I'm drawing is a tree edge, right? Then we went to D. Then we went to E, and then F. At which point we started backtracking, right? We backtracked from E up to D. And then we saw that, oh, now you can go over to G, right? And we traverse that edge so it's part of this tree edge here. And this is why we call them tree edges. From G, we went over to H. If I only look at those edges, it forms a tree, right? All of these other edges in the graph, I never traversed them in the DFS. Those aren't part of this tree, right? They're different types of edges. So let's go ahead and label those instead. I see that I can go from A to C, right here. So A to C. That looks like a forward edge because it is connecting an ancestor to a descendant in this tree. But guess what? It's undirected. So it's also a back edge, right? So in an undirected graph, forward edges, back edges, they're the same thing because there's no orientation. Let's see if we can find some others here. And I'll go ahead and keep marking them so that I don't miss any. A to H. There we go. There we go. That's that one right there. That's also a back/forward edge because A is an ancestor of H. H is a descendant of A in the tree. Okay. Keep going here. D to B. There we go. Also a back/forward edge, same thing. B to G. B to G, same thing. Forward edge, back edge. DF. D to F. And I to F. I to F. Back edge, forward edge. All of these are back edges and forward edges. Okay. Now, what about, let me use a different color here. There we go. What other kind of edges could there be? What about E to H? Right? Could we have that edge here? Let me think about that for a second. Right? What if it were over here? E to H. Where's E? E to H. If we had had that edge, when we backed up from F, we would have gone to from E, and we were at E here. If that edge had been there, we would have actually visited H and then gone over to G from H. So it would have led to a different tree. So no, that's not possible. We'd have a different configuration here. What about, F to H? Well, same story there. If it were there, then we would have just gone to H immediately. Right? So otherwise, if it did have this kind of configuration here, if it did connect, say, cousins, right, then that would be what's called a cross edge. Are cross edges possible in a DFS forest? We'll think about that for next time, right? What if there were, right? Could you go from G to E or E to H or F to G? At least in these limited cases here, then that means that you would have traversed them already, right, in your DFS forest. But otherwise, this ends up being our DFS tree. Right? And all these red edges, that's not part of the main tree, but if you drew them, then it wouldn't be a tree. But if you drew them, then you can determine, is this a back edge, is this a forward edge? But before we stop today, what does the presence of a back edge or a forward edge imply? So I can go from I all the way down to F. Oh, but there's also a back/forward edge between them. Guess what that thing is? A cycle, right? So you can use this idea. You can use these artifacts to detect cycles. Right? So let me go ahead and go back to our notes and note that down. Right? In an undirected graph, I'll just spoiler alert here. In an undirected graph, in fact, let me go ahead and make these as observations. There we go. In an undirected graph, only tree/back edges are possible. Right? Forward are the same as back because it's unoriented, and cross edges would not exist. Right? Star there. However, in a undirected, actually no, sorry, scratch that. In an undirected graph, the presence of a back edge implies a cycle. Right? Presence. There we go. What about directed graphs? We have enough time to talk about it here. In a directed graph, back edges are possible and indicate a cycle, a directed cycle, I should say. Right? So imagine the tree. You're going down in the tree, and then there's a back edge to an ancestor in the tree. There's your cycle. A forward edge no longer implies a cycle anymore in a directed graph. Simply because you can go from A to B to C to D, and you can also go from A to D. That doesn't necessarily mean you can get back to A, right? Unless that edge is also there, right? In a directed graph, all four possible edges, all four types of edges, are possible, right? And I'll leave it as an exercise to come up with this very simple example in which, in fact, we've got enough time. Let's just do it. Let's try to come up with an example here where the DFS would result in all four types of edges. Okay. In a directed graph, I should say. Right. Remember, only two of them are possible in an undirected graph. Right? So let's go ahead and create something that I know that these are all going to be tree edges here. I'll label this as 0, 1, 2, and 3. Right? That will necessarily produce 0, 1, 2, and 3. Now what we want is a back edge, say 3, 2, 1. So all we have to do is put that over here, 3, 2, 1. And here immediately you can see that cycle, right? Back edges imply cycles, okay? I want a forward edge. So let's go ahead and forward an edge from 0 to 2. Right? And to do that, I will just draw this vertex right here, 0 to 2. And that gives me a forward edge. Right? I'm going to have to write another vertex here. Let's go ahead and go with 4. And there we go. 4. There. I did that because now I want a cross edge between these two. 3 is not a descendant of 4, nor is 4 a descendant of 3. They're cousins, or however you want to depict that, distant relatives. But how would I have to orient this? What if I went from 3 to 4? If I oriented it like that, then it would have ended up being part of my DFS tree. Because from 3, we can still get to 4 with a directed edge, and that won't produce this DFS tree. But what I can do is I can orient it the other way. Right? If I go from 4 to 3, then in the DFS forest here, when I backtrack, 3 is done, I go forward to 4, and I see that 3, well, it's already been colored black because I've already visited it. So here's a very simple example of just 5 vertices where you can get all types of edges. Again, this is a cross edge, this is a back edge, and this is a forward edge. And all the black ones are just regular tree edges. Right? I'll leave it as an exercise to come up with a smaller graph where you get the same configuration of all 4 types represented. Right? All right, then you have some work to do. Be sure to get started on assignment 3 immediately. We've covered at least, for the written portions, we've covered enough that you can get started on those, if not complete them. For the programming, of course, what you'll want to do is you'll want to install whatever you are going to use, networkx, on your local computer if it's not there, or work from CSE. And you're going to want to write your parser so that you can read in the input files and build your graphs. Right? Yeah, even if you have, and then of course you can start programming DFS immediately. Right? So good luck.